Question 8. A 3 kilogram mass attached to a string 6 meters long is to be swung in a circle at a constant speed. It's important, constant speed, making one complete revolution in 1.25 seconds. Determine the value that the breaking strain of the string must not exceed if the string is not to break when the circular motion is in horizontal plane and the vertical plane. Now, firstly, when looking at this, we are going to be using these formulas over here. We're actually given the T. This T here is your 1.25 seconds, and we are given the R, which is 6 meters. So we're going to be using that formula over there. So let's just write that in. We've got our A is equal to 4 pi squared R over T squared. Now, in looking at the horizontal plane, if I can just try and draw it in 3D, which I'm not always too good at doing, we've got this is doing in circular motion, and it's got a radius of 6 meters. Now, this object going around, it's going with a certain velocity around certain speed. The forces on that, well, there's going to be a force downwards which is equal to mg, but that is going to be cancelled out by the surface that it's moving on. So that's going to be also mg. So in the vertical, there is going to be a cancelling out of those forces. So the only unbalanced force acting on this is your tension. And that tension will equal m times acceleration, which is 4 pi squared R over T squared. Perhaps I should call this a force. I should use the word force and not tension so that we don't get mixed up between this T and the T for tension. So we just need to put that in. We're going to get 3 times 4 pi squared times 6 divided by 1.25 squared. Now I can do that on the calculator here. So we're going to get 3 times 4 times pi squared, mustn't forget the squared, times 6 divided by 1.25 squared. Enter. And we get this value there, 454.79. So my tension and the force is going to be 454.8 newtons. So let me just write that up over here. 454.8 newtons when you're in the horizontal plane. Now, when I look at the situation now in the vertical plane, it's slightly different. So in the vertical plane, we've got it going around in a circle like that. We actually get a situation, I'm going to look at it at that point over there and also look at it at that point over there. This is when you get gravity acting on. So let's say it's moving in that direction, the velocity is like that. You would have a force down here which is equal to mg, and you would need to have in the string, there would need to be a force not only of mg to cancel that force, but also of mv squared over r, or this formula over here, your m 4 pi squared r over t. You need that force also to cause the centripetal acceleration. So the centripetal force needs to be there also. So the mg cancels that, and you just left with that. So you notice here that at the bottom here, you're actually going to get a maximum tension. This is going to be the point. The bottom end of the swing will be a maximum tension in the string. When you're at this point over here, you've got your mg downwards, and that will actually add to cause the centripetal force. So at that point over here, you actually get a lessening. When it's at the vertical position, say at point 2, you get the smallest t, T is small, comparatively small. At this point over here, this one over here, T must be big. Your tension in your string is large. So, if I put that into my formula, then I'm going to therefore have that my tension, or I'll use force, is equal to mg plus m4 pi squared r over your time, like that, your time squared. So we know what this over here is over here. We've already worked that out. This is what we worked out there. So your force is equal to mg, which is going to be, we were told 3, and I'll use times 10, plus this over here, which we've already calculated, we calculated over there, is equal to 454.8. So it's going to equal 484.8 newtons will be your tension, your maximum tension, which will be at this point here.